In this lecture, we're going to discuss Paleozoic life, in particular, Paleozoic vertebrates. Now, just to be clear, there are many invertebrates alive and thriving during the Paleozoic. We know that the Cambrian explosion happened at the beginning of the Paleozoic, and those were mainly invertebrate organisms with exoskeletons. And so they continued to increase in numbers and diversity throughout the Paleozoic. But what we're going to focus on in this lecture is vertebrate evolution through the Paleozoic. Because it's during the Paleozoic that vertebrates make large advances in evolution. We'll first talk about we'll start with the first major group of vertebrates, the fish. Look at the jawless fish, Ostracoderms, and the primitive jawed fish, bony fish, and lobe-finned fish. Then we'll move on to amphibians, and we'll discuss the difficulties of moving onto land and look at the earliest amphibians. Then we'll move on to reptiles, look at the differences between reptiles and the amphibians they evolved from. We'll discuss stem reptiles, fin-back reptiles, and then finally mammal-like reptiles, known as the therapsids. Now this is one of my favorite lectures in this course because it really it helps illustrate our place in the tree of life. And by the end of the lecture, you'll learn where different features you have in your own body, who evolved them first, and thus who you inherited them from. So we'll start with a question: what is this? It's not easy to place this in a box. This organism, is it a fish? Is it an amphibian? You'd say it looks like the basic body plan of a fish, but it has a flat head where fish's heads are usually more vertical. And you see its fins are being used to support some of its weight, which is interesting and not commonly associated with the fish. So we will answer the question as to what this is in the lecture. So vertebrate evolution. So during the Paleozoic, we start back in the Cambrian, 545 million years ago. And we discussed the Cambrian evolution, the Cambrian explosion, where complex animals with exoskeletons evolve. And during that lecture, we mentioned that some of those primitive vertebrate organisms evolved during the Cambrian as well, such as Tiktaalik. So this is one of the first known species of organisms that are vertebrates, that have a spinal cord that's surrounded by bones. And so it's organisms like this that all vertebrates today have descended from. So this is the ancestor of all vertebrates alive on the planet today, and all vertebrates that have existed in the past are now extinct. And so from those early vertebrates, the first major group to evolve were the fish. So fish appear in the fossil record in Ordovician, and they are around for the remainder of the Paleozoic, and as we all know, they're still around today. So what is something that most fish, amphibians, reptiles, mammals, and birds have in common? Is it A, warm-bloodedness, B, 4 legs, C, scales, or D, jaws? Well, we know that amphibians, reptiles, and most fish are not warm-blooded, they're cold-blooded. We know that most fish don't have 4 limbs. There's many amphibians, mammals, and birds. Well, mammals and birds don't have scales. Amphibians don't have scales. So it's jaws. Jaws is the feature that all vertebrates have in common. And so besides their vertebrate itself, the bones around their spinal cord, jaws are one of the most primitive features of vertebrates. In fact, the first vertebrates did not even have jaws. The Ostracoderms were a line of jawless fish, and so they appear right at the end of the Cambrian, beginning of the Ordovician, and they go extinct by the end of the Devonian. And from them, primitive jawed fish would evolve, and from them, bony fish, which include lobe-finned and ray-finned, which we'll talk more about. And also, cartilaginous fish evolved from early primitive fish as well. So these jawless fish, the Ostracoderms, they were the most primitive type of fish. Many of them still had armor. Why did they have armor? Well, remember, because vertebrates evolved from invertebrates. And so even though they have the beginning, they have an endoskeleton, but they still have some of the exoskeleton features of their ancestors from which they evolved. And so many of these early jawless fish still had that exoskeleton. It's armored an exterior of their body. Most of them lived on the sea floor because that's where their invertebrate ancestors lived. You think about most invertebrates in the ocean today, they're living on the sea floor. As far as crustaceans, like crabs, lobsters, so forth. Most mollusks, not all mollusks, the bivalves like clams, oysters, mussels, and the gastropods, snails, I guess the squid and octopi, they don't live on the sea floor, at least a lot of them, they swim. But most invertebrates live on the sea floor. So it makes sense that the first vertebrates that would evolve from invertebrates would live on the sea floor too. And so they feed similar to those invertebrates. They don't have a jaw. They would just take in organic matter, filter it out of the sand, out of the water, and that's how they would find their food. Now, jawless fish are not extinct. There are several species of jawless fish still alive today. In this figure on the right, there's a man holding a lamprey. You can see lamprey does not have a jaw. Now, the lamprey does not feed on the bottom like its ancestors did. Lamprey is actually a parasitic fish where it attaches to the side of another fish, uses these little teeth to scour the skin, and then the fish begins to bleed, and it feeds off of the blood of the host fish. So from the Ostracoderms would evolve primitive jawed fish. Now, the best working hypothesis, or I guess I should say it's a theory of where the first jaws came from, is that the first couple gill arches, which gill arches are these bones that fish still have today, on which the gill membranes are attached. These first couple gill arches evolved into jaws. Now, as we'll see, the evolution of organisms, we don't see features just pop out of nowhere. Features evolve from already existing features that are modified and repurposed for a new job, a new function. And so this, we see this in the fossil record, how these gill arches over time, they slowly change, and there's this gradual transformation from the gill arches into primitive jaws. And it's thought that these first jaws were not for feeding, but actually in order to have control over opening and closing the mouth to control the flow of water. Because as you know, in order for fish to breathe, they have to move water past the gill membranes. So like sharks, you ever hear sharks have to constantly swim because they have to constantly be having water move through their gills, where other fish, they open and close their mouth while remaining stationary, pushing water through their gills. So in order to open and close your mouth, you need a jaw to push that water through your gills. So having a jaw would allow fish to not have to swim and still breathe. But there's a secondary purpose for these jaws. Now they can act they can be used to acquire food. And so this would allow fish to become active predators. And so we see primitive jawed fish arrive in a fossil record, appear in a fossil record around the Silurian, and such as the Acanthodonians. So they have teeth in their jaws, and they have reduced body armor compared to the jawless fish, but they still have body armor. And these Acanthodonians are probably the ancestors of modern day bony fish and cartilaginous fish. Also, at the same time as the Acanthodonians is another group of primitive jawed fish that went extinct were the Placoderms. So plaque meaning plate and derm skin. They had plate skin, so they still had pretty heavily armor plating. There are several species of Placoderms. You see a couple of them on the left-hand side there. The image, the colored image on the right, that is Dunkleosteus. Dunkleosteus is the largest known fish to ever live in the ocean, being larger than 12 meters long. Right, so this is larger than the whale shark, which is currently the largest fish in the ocean. 12 meters, that's a meter's approximately similar to a yard. So that would be like around 36 feet. So that's a big fish with this large armor plating. It was a ferocious predator. It was the apex predator of its day. So it would have been a very scary time to be in the ocean. There were these 30 to 40 feet long armored predatory fish were swimming around. So what was the first key evolutionary development of fish? Was it the vertebrae, large size, or jaws? As we saw, it was their jaws, right? Jaws would be so successful that they would be passed down to amphibians, to reptiles, to fish, reptiles, to mammals, and to birds. And so from these primitive jawed fish, in particular the Acanthodonians, bony fish evolved, along with cartilaginous fish. So cartilaginous fish include modern day sharks, skates, and rays, also another group called chimeras. They're called cartilaginous fish because they don't have calcified skeletons. Their skeletons are composed of cartilage. Now, if you ever think back, you never see a skeleton of a shark. The only part of a shark you see is its jaws, because the jaws are actually the only calcified bone in a shark's body. The rest is cartilage. So that's cartilaginous fish. They have cartilage skeletons. They don't have calcified bone. The other group of fish that evolved from the Acanthodonians are the bony fish. So bony fish are those that have calcified bone. So that is more easily preserved. It doesn't decay away as quickly, so we find fossils of these bony fish. Right, so these ones. And so bony fish appear in a fossil record in the Devonian. And there's two groups of bony fish. There's the lobe-finned fish and the ray-finned fish. And you can see the difference is in the primary difference is in their fins. Ray-finned fish have bones that extend outward from their bodies like rays. Then there is skin stretched up in between those bones, and that's supported by the bones, and that makes the fin. Where lobe-finned fish, its lobes, its fins are constructed differently, where it actually has articulated bones and muscles. Articulated means that they're put together or they fit together in a certain way, and they work together. So they fit and work together. And so you can see these multiple bones arranged in here. And if you look at it, it's the same structure as we have today. There's the upper arm bone, the humerus, the forearm bones, wrist bones, and the digits. And so this is where the structure, the four-limb structure of all vertebrates first comes into existence in these lobed fin fish. So here are some pictures of some ray fin fish. When you think of fish, that's typically the type of fish you think of. okay, where their fins are supported by thin bones that spread away from the body. They dominate the seas in the Mesozoic and they still continue until up till today. For lobe-finned fish, many went extinct, but some are still around. Their fins are composed of articulated bones and muscles. As I said, you can see they're thicker, right? They have bones and muscles inside of these fins. And so here's two examples of present-day lobe-finned fish. And so it's from these lobe-finned fish that one branch of them would lead to amphibians, evolve into amphibians. And so how did this happen? Well, if you think about it, having these articulated bones and muscles in their fins would allow them to pull themselves into shallow water, shallow coastal waters, maybe along a beach or maybe up, in rivers. And why would they want to do this? Well, they could be moving into these shallow coastal waterways to find food that other fish don't have access to because they can't go into that shallow water. Or they could be attempting to avoid predators, larger predators in the deeper waters. Or they could be moving to shallow water to breed. So maybe it's safer to lay their eggs in that shallow water where there's less predators. So for whatever reason, these group of lobe-finned fish are spending more and more time in shallow intercoastal waters, and they begin to pull themselves out of the water, for the same reasons. There's to find food. Maybe they're preying on insects or other invertebrates that are outside of the water. They're avoiding predators in the water. They weren't reproducing out of the water. We'll learn that's one of the limitations that reptiles would overcome, is the ability to reproduce outside of water. So that group of lobe-finned fish would evolve into amphibians. Okay, so plants and insects are already on land, and so you can see the wealth of food. So all invertebrates, all fish are currently in the water. There are no vertebrates on land. Okay, so vertebrates are latecomers. So these amphibians, they're the first vertebrates on land, and so they have access to this food source. Not only that, but there's no predators. There's no other organisms that are going to eat them besides themselves. Amphibians can eat other amphibians. So what is the most recent evolutionary ancestor of amphibians? Is it cartilaginous fish, ray-finned fish, lobe-finned fish, reptiles, or jawless fish? So ask yourself, which of these do amphibians share the most recent evolutionary ancestor with? And that would be the lobe-finned fish. So these lobe-finned fish are the closest living ancestors to amphibians. So what are some of the difficulties for moving from water onto land? Well, we can see early amphibians overcoming those difficulties. We compare their skeleton to that of the lobe-finned fish from which they evolved. Right? So one issue is drying out. Okay, so desiccation is a real threat whenever you're outside of water. And so how do amphibians overcome that problem? Well, we know that amphibians often appear slimy. Well, that slime is a mucus that they excrete that helps retain moisture, though it's not perfect. And for that reason, amphibians still need to live in very humid environments or near water because they can't be completely away from water or else they will dry out. And then they're able to blink their eyes to re-moisten their eyes, which fish don't have to do. Reproduction. Reproduction is something that amphibians still rely on the water for. because their eggs do not have watertight membranes. And for that reason, if they laid their eggs on land, which they'd want to because there's not as many predators on land to eat their eggs and their young, their eggs would dry out. So some amphibians can lay their eggs outside of water, but it's only in very humid environments like rainforests and so forth, where the eggs don't dry out because of the high humidity. So we have drying out, reproduction. These are challenges for moving on land. The effects of gravity and also breathing through lungs and not gills. So what features are already present or needed only slight modification in lobe-finned fish for them to move onto land? Well, we have a backbone and limbs for gravity. And it's thought that lobe-finned fish have rudimentary lungs. That's why a present-day lobe-finned fish, lungfish, is called a lungfish. It's thought that the swim bladder of fish evolved into lungs. Mainly it's thought that because lungfish don't have a swim bladder, they have lungs. And so these lobe-finned fish, like Tiktaalik here, it had the backbone and the limbs to support its weight and the force of gravity, and it had lungs to extract oxygen from air. This is a picture of Tiktaalik, which is thought to be one of the first vertebrates to really call its home, or most of its home, the land. And so it had finger bones in its fins. It had flexible wrists, a flexible neck, nostrils, and expandable ribs. You need expandable ribs so that your lungs can expand and contract, take in an inhale and exhale. So those are all features that Tiktaalik had that were advantageous for living on land. You notice fish can't turn their necks. They don't have flexible necks. That's something that terrestrial vertebrates have. Nostrils. Fish don't have nostrils for taking in air. And these flexible wrist bones and finger bones help moving on land. Where features that Tiktaalik had that were still well adapted for water included fins, scales, their primitive jaw, their streamlined body, and their long tail. So Tiktaalik really had features for both that were useful for both living on land and still living in water. And so here is the bone structure of the first lobe-finned fish. Here is a fin with a wrist, like Tiktaalik. And then here is a limb, so you can see the progression, how it's the same bones, just being modified over time. So did Tiktaalik evolve with the goal of future living on land? Answer A is yes. Why else would it have characteristics that are so useful for living on land? Answer B is no. It evolved to fit into its environment, and its characteristics happened to be useful for descendants living on land. Also, the correct answer is no. Remember that no evolution is intentional. Organisms do not intend to evolve. Evolution is driven by the environment. And so this organism was living in an environment where the features it already had were useful and selected upon, so they become amplified over the generations. So looking at these earliest amphibians, so Tiktaalik was still technically a fish, but from organisms like Tiktaalik, these early amphibians would evolve. So you can see illustrations of Ichthyostega, Acanthostega, and Eropes here. And then on the right, you can see the forelimbs of them. Now they're not in order, right? This is Acanthostega, so this goes to this one. This is Eropes, so it goes there, and this is Ichthyostega, so it goes there. Looking at their forelimbs, can you tell which one is earlier or more primitive and which one's later, more advanced? So Acanthostega it has 8 digits, 8 fingers. Ichthyostega has 6.5, and Eryops has 5, right? 5, that sounds familiar. But you can see there's a reduction in digits. Along with that, the arm bones, the humerus and the ulna and radius, they increase in length as well. And also you can see the wrist becomes more complex. So obviously, moving in this direction, the forelimb is becoming more advanced and more well adapted for locomotion on land. And so Acanthostega is the more primitive, Ichthyostega is in the middle, and Eryops is the most advanced of these 3 amphibians. Now, why the reduction of digits? Well, many digits creates a very broad paddle or for swimming through water. So there would be skin stretched in between the digits. But whenever you're moving on land, that many digits is cumbersome. You can imagine you could stope them, or more importantly, you could break one of those many digits. If you break a digit, that inhibits your motion and that reduces your chance of survival. So the fewer the digits, the less liability. So as we'll see that, as we go on, organisms that run very fast or move very quickly, they have a reduction in digits. Like for example, horses and deer, they only have 1 digit to reduce the liability of breaking a digit. So it comes to 5 seems to be what works best in nature, because 5 is enough digits to provide stability and dexterity, but it's not too many digits to create a liability that you break a digit very often. So we find these amphibians evolving, and we find these fossils of early amphibians that are adapting more and more to life on land in the Devonian. And so what did the environment that they lived like look like? Well, so these amphibians lived in environments likely, or what you see here. So these intercoastal waterways, so these rivers moving up from the ocean into land, surrounded by dense swamps. And these amphibians would live around these rivers and swamps, eating insects and other smaller amphibians, and maybe even hunting for fish in the water. And so we find fossils of these amphibians in these sediments that were deposited from the erosion of the Acadian Mountains. If you remember from the Paleozoic Earth lecture, that Laurentia, Baltica, and Avalonia collide to form Laurasia and the Acadian Mountains. And as those Acadian Mountains weather away, all that sediment is being deposited around here. And deposited and found in those sediments are the fossils of these amphibians from the Devonian. So labyrinthodonts, they are a group. They were pretty much the apex amphibians. All right, they were most of them were greater than 2 meters in length, which is impressive, right? They're about the size of a compact car. They lived in swamps and streams, ate fish, vegetation, insects, and smaller amphibians. They are abundant in the Carboniferous when there was many swamps. They declined in the Permian, and they would evolve into, the line of them would evolve into reptiles. So these labyrinthodonts, these were at one time during the Carboniferous the dominant land vertebrate. So if you'd go back 300 some million years ago and say, what is the vertebrate like? Like, what is the apex predator on land? As far as vertebrates go, it would be these amphibians. It's hard to imagine an amphibian the size of a Toyota Prius, but that was them. I mean, it makes sense though, because they were the only vertebrates on land. So they were the top of the food chain. So comparing the skeletons of lobe-finned fish and the most advanced amphibians, we see that the bones and the fins have been completely repurposed into limbs for walking on land. We have longer bones to generate a further separation between the body and the ground. We have these digits for stability. The forelimb is attached to the backbone through a shoulder, and a hind limb to the back attached to the backbone through a hip to provide support against gravity. We see the skull is reduced in size, so there's less bone because you don't have to support that weight under the force of gravity. Then also we have these expandable ribs for breathing. And so looking at lobe-finned fish, we can see the bones that are present in our arm, the humerus, ulna, and the radius, right? And these are the same bones in the early amphibians. And so it's so cool to look at the structure of the bones inside these lobe-finned fishes and see that they're the same exact bones in our arms, right? And that they've been passed down from these lobe-finned fish to amphibians to reptiles to us. So we can see who we inherited these bones from. So to answer our question we started with, what is this organism? It is a fish, but it's on its way to becoming an amphibian. So it is the last line of this evolutionary lineage to be considered a fish, and it's the most recent fish ancestor of amphibians. So we talked about the evolution of fish to amphibians. But what about amphibians to reptiles? So like we said, amphibians need to live around water so they don't dry out and so they can reproduce, where reptiles, they do not. Reptiles are not tied to the water, and they can reproduce outside of the water. So what are the differences between amphibians and reptiles? We discussed some of them, but looking back millions of years ago, some of those are a little bit hard to discern. So the more important question is, what differences between reptiles and amphibians can be recorded in the fossil record? Eggs is one of them. Amphibians need to lay their eggs in water. They have no watertight membranes, and so they decompose fairly quickly. Where reptiles, they developed amnio eggs. So this allows their eggs to develop on land, because an amniotic sac is a watertight membrane around the egg. And so birds and mammals would inherit this amniotic sac from reptiles. But this is the evolutionary leap that allows reproduction to come out of the ocean and onto land. And so because these reptiles, they're hatching from their eggs on land, they don't have to go through a larval stage that the amphibians had to, where they hatch in water, so they have to be adapted for water, but then metamorphose into a body that's suitable for land. So reptiles, they evolve the lack of this larval stage, and so they hatch as miniature adults. So unlike amphibians that have a tadpole or a polywog, they bypass that larval stage. So here we see a cluster of amphibian eggs laid in the water, and here are reptile eggs. So these eggs, in order to be on land, the amniotic sac is very important, right? If it's punctured, then the water and the moisture will seep out, and the developing embryo will perish. And so it's important to have a protective layer around that amniotic sac. So eggs have a leathery or calcified layer around the amniotic sac, which allows it to be more likely to be fossilized. So you see fossilized eggs of reptiles. That's one evidence of the difference. One piece of evidence of the difference between reptiles and amphibians we find in the fossil record. We find amniotic eggs, which allows reptiles to reproduce on land. What about their skeletal structure? We're looking at their skull. They have stronger jaws, and they have teeth better suited for biting food. So looking at comparing the lobe-finned fish to the early amphibians to the modern reptile, you can see there's a general trend. The jawbone becomes larger. And remember, we said, what does that tell us? Well, larger muscles are more powerful muscles. And in order to support the force that larger muscles are capable of producing, you need larger bones. So the larger jaw suggests that reptiles had a stronger bite. And the more well-adapted teeth for biting food makes reptiles better predators, and they have expanded diets compared to amphibians. Also, you can see the amount of bone in the skull decreases. You can see where the lobe-finned fish, it's very heavily, a very dense and cumbersome skull, where amphibians, the skull is a little bit less bony, but you can see that there's significantly less bone in the modern reptile skull. Why is this so? This is becoming more efficient. So we have bone where we need it for the structural integrity and to serve certain purposes like protect the brain. But we also don't have unnecessary bone that adds weight, that makes it more cumbersome for supporting its weight on land. So now looking at it was the skull. Now looking at the limbs and the vertebral construction, reptiles are better suited for movement on land. So primitive amphibians, they had these short limbs that did not give them much space between the ground and their bodies, where for reptiles, they have a little bit longer limbs that provide them more clearance between their ground and their bodies. Now, why is this clearance important? Well, if you can imagine, if you're walking on the ground, and there's not a lot of clearance between the ground and your underside, then your underside is going to get injured. It's going to get scraped and cut. And the more you get scraped and cut, the higher the chances, the more opportunities you have to become infected and thus die. So, evolving longer limbs to give you more space between you and the ground, more clearance, is advantageous. Also, longer limbs allows for the organism to move faster. So it's more nimble and it can travel faster on land. So this brings us to stem reptiles. So proto-rothirids. So I'll ask one of these similar questions as I did in the beginning of the lecture. So looking at the skeletons of these organisms, and what are they? Are they reptiles or are they mammals? It's hard to answer because they look weird. They don't look like what we typically think of mammals look like, but at the same time, they don't look like reptiles. They look too stocky for reptiles. But they also look too kind of cumbersome for mammals. Well, we'll answer that question as we go on. So these stem reptiles, it's a loose grouping of the earliest reptiles. The oldest are found in the early part of the Pennsylvanian, which is the Pennsylvanian is the latter half of the Carboniferous. And they are small and agile. They fed largely on grubs and insects, but because they are better suited for locomotion on land, and because they can reproduce on land, they began to displace amphibians in the latter part of the Paleozoic. So they're advanced eggs with amniotic sacs, allowing them to reproduce on land. Their more advanced jaws and teeth and their better ability to move on land gave them a competitive advantage over amphibians. So thus, as natural selection will tell us, they begin to displace these amphibians. And so the fossils of amphibians begin to decrease in number during the latter part of the Paleozoic, and the fossils of these early reptiles begin to increase. And so from these stem reptiles, a large number of vertebrates would descend. That's why they're called stem reptiles, because a lot of evolutionary lines of vertebrates stem from them. So we have marine reptiles like the ichthyosaur and the plesiosaur, which we'll talk about. They lived during the Mesozoic and they're now extinct. We have other lines that would lead to snakes and lizards, and a line that would lead to turtles. A line would lead to archosaurs, which archosaurs include the only species group of archosaurs alive today are crocodiles and birds. And then they also lead to another lineage, these finback reptiles, which I'm sure you've seen these in pop culture. Most people refer to them as dinosaurs, but more interestingly, these finback reptiles, from them would evolve these mammal-like reptiles, and from those would be mammals. So these stem reptiles are our ancestors too, and our evolutionary lineage stems from them. And so we're going to focus in this course on this evolutionary lineage and this one. We're going to talk about the archosaurs mostly during the Mesozoic, because that's whenever the dinosaurs are the dominant vertebrate on land. We'll talk more about the mammals during the Cenozoic, because that's whenever they dominate. But for now, we're going to talk about this section of the mammalian evolution, because that takes place during the Paleozoic. So is this animal a dinosaur? I know I answered this question already. Most people associate it with a dinosaur, right? But the answer is no. Now, how do we know that? Well, these are finback reptiles known as pelycosaurs. And they fall in the evolutionary lineage that, that mammals would derive from. And we find these finback reptiles, these pelycosaurs, in the Permian, so the end of the Paleozoic. And there was many different species of pelycosaurs. The Dimetrodon is one of the most common and most well known. So they evolved from the stem reptiles. They were dominant at the end of the Paleozoic, but they went extinct at the Paleozoic mass extinction, at the end of the Permian. They had a sail or fin on their back. Now, paleontologists believe that this sail likely served one of two purposes, or possibly both, as a thermoregulatory device. That is the current consensus. That we could see from the bones in this fin that there were blood vessels that surrounded it. So it's thought that they might have pumped blood up into the sail, and they can turn their fin into the sun and allow it to catch the rays of the sun in order to warm their blood. And if they needed to cool their body, they can face their sail into the wind, where the wind can blow past it, removing the heat from their blood, thus cooling their body. It's also thought that the sail could have acted as a sexual display to attract mates, similar to the feathers of a peacock today. So from these finback reptiles, the pelycosaurs would evolve therapsids. Now, the therapsids are the mammal-like reptiles. And so these skeletons, these fossils, they belong to therapsids. These therapsids quite likely had fur and were semi-warm-blooded, and very common at the end of the Paleozoic during the Permian. So these would have been the dominant vertebrates. So these are reptiles that are becoming mammals. You can see how the limbs are moving out from the side of the body. You imagine an alligator, how it walks. Its forelimbs and hind limbs stick out from the sides of its body, and so it kind of wiggles back and forth. And its spine, it bends side to side as it walks. Where these therapsids, its limbs are moving underneath its body to give it more clearance between the ground and its underside, and to allow it to move faster on land. And so the more vertical, as I said, position of the legs gave it greater flexibility and increase its ability to move on land. And then we also see the evolution of different shaped teeth. So this is a hallmark of mammals. Mammals are the only vertebrates that have specialized teeth. You know, we have molars, bicuspids, incisors, canines, right? So no other species of vertebrate has specialized teeth, and we see this starting in the finback reptiles and continuing into the therapsids, these specialized teeth. And what this does is this expands the diet even further. Now we can have omnivorous organisms that eat both vegetation and are carnivores as well. We also see a reduction, just like we saw of bones in the skull, just like we saw from the lobe-finned fish to the amphibians, and from amphibians to reptiles. We see the same thing from reptiles to mammals. Where in the Paleozoic, we have several bones that compose the lower jaw. And so this bone right here, the dentary, it would become the dominant and sole bone of the jaw of early mammals, where these other bones are in the lower jaw, the angular, the articular, which is a bone in the jaw hinge, and then this quadrate is in the skull. Over time, these bones shrink and move into the skull, and those bones actually become the inner ear bones, you know, like the stapes and the anvil. And so what's the advantage of having a larger jawbone made up of one bone? Well, it has more strength, which means we have an expanded diet. Which of the following are we as humans most closely related to? Dinosaurs, birds, finback reptiles, amphibians, or lobe-finned fish? So remember, when we ask the degree of relation, we're asking which of these do we share the most recent common ancestor with? Well, that would be the finback reptiles. So the Dimetrodon, we go back, and it was like this. We're more closely related to this creature than we are to birds, than we are to fish, than we are to reptiles, because Dimetrodons would evolve into therapsids, and therapsids were mammal-like reptiles. But unfortunately, so by the end of the Paleozoic, right here, so here's the Paleozoic, the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, and Permian. By the end of the Paleozoic, mammals are set, they're poised to take over as the dominant land vertebrate. But then something happens. The Permian Triassic mass extinction, about 245 million years ago. And it is hard. It is very hard on warm-blooded animals. And so therapsids are hit hard. And they largely go extinct. Those smaller species do make it through. They do eke through the Permian Triassic mass extinction. And thankfully for us, they do, because if they didn't eke through this mass extinction, we wouldn't be here today. Mammals would have never come. Maybe they would have evolved at a later date, a later time, but you know, our evolutionary lineage would have been cut off completely. It's like cutting the branch off the tree. But fortunately, just one little branch, one little sprout made it through that mass extinction, and it was able to hold on for the next several, actually about 200 million years, while reptiles dominated. So the Permian Triassic mass extinction, it was selected more against large warm-blooded animals and less against cold-blooded animals. So that's why the reptiles, even though they were in the process of being displaced by the therapsids, they inherited the earth after the Permian Triassic mass extinction, because this extinction event was not as hard on them. Now, in the supplemental videos in this module, there's a TED Talk by the paleontologist Peter Ward. And he talks about this Permian Triassic mass extinction. He talks about the extinction of the therapsids. And he gives, you know, one of the best working hypotheses as to what the mechanism was for this mass extinction that selected hard against warm-blooded mammals, but not against cold-blooded animals. And so I recommend that you watch that video, and you'll actually have to talk about that video in the blog, so you'll need to watch that video. It's not too long. And so it's very, very interesting. And if it wasn't for this Permian-Triassic mass extinction, the dinosaurs, as we know them, probably would not have been, right? And as you'll see in Peter Ward talks about, this mass extinction is thought to have been caused by basically there's a large amount of volcanism in what is present-day Siberia, which produces a lot of CO2. Yeah, CO2 warms the climate. And it warms the climate to the point where the oceans, the surface of the ocean is so warm that it layers or stratifies, and the ocean is no longer circulating, no longer turning over. And what happens is the bottom of the ocean is no longer provided any oxygen, because water from the surface, where oxygen is added to the water from it dissolving into water from the atmosphere, and photosynthetic organisms produce oxygen and put oxygen to the water to the surface. That oxygen-rich water from the surface no longer makes it to the bottom of the ocean, because the ocean is stratified, layered. And so the bottom of the ocean becomes it depends, hypoxic or hypoxia, which is the lack of oxygen. And there's this bacteria that thrive in poor oxygen environments, and they produce this gas called hydrogen sulfide as a metabolic byproduct. And so hydrogen sulfide begins to accumulate in the depths of the ocean, and eventually it begins to burp out of the ocean. And hydrogen sulfide is very toxic to warm-blooded animals, and not so much cold-blooded animals. And so that's the hypothesis, that how this mass extinction, it pretty much wiped out all these warm-blooded animals, but most of them, these large warm-blooded animals, but cold-blooded animals made it through. So, this Permian-Triassic mass extinction, not only did the climate warm, so it did have a hard impact on not just warm-blooded, but other organisms as well. It just was especially hard on warm-blooded, large warm-blooded organisms. But, this climate change, it happened over the course of several million years, right? And then also acidified the ocean, as I mentioned in the previous lecture. And so that more acidic ocean and the warmer climate, that's what caused mass extinction. And as I said previously, we're seeing the same thing happen today. Our climate is warming and our ocean is acidifying from us producing CO2 through the burning of fossil fuels, and by cutting forests, which typically would absorb CO2. And the scary thing is, this Permian-Triassic mass extinction was the largest extinction in Earth's history. It's caused by the same process that's occurring today. The only difference is the process is occurring today is occurring at a faster rate than it did in the lead up to the Permian-Triassic mass extinction. So, as you can see in the late Permian, over 50% of the species on the planet went extinct. Right? That's scary, right? That's real serious. And so that we have to heed the warnings that the geologic record has for us, that there is precedent. We know what happens when the climate warms quickly and the ocean acidifies quickly. We know what happens, and it's happening even faster today. So if people, they talk about climate change, if they sometimes sound alarmist, they have every reason to be alarmist, because it is bad news for life on the planet. Will Earth be destroyed? Will life on Earth be eradicated? No. Organisms will survive. But most will die. A lot will die. But organisms will survive, and the Earth will continue on as it always has, and life will continue on as it always has. It'll just be much different. The Permian-Triassic mass extinction wiped clear the therapsids and allowed the dinosaurs to take reign. And as we'll learn later, the KT mass extinction right here, that ends the Mesozoic, that wipes the dinosaurs out and allows the mammals, which have been hanging in the background during the Mesozoic, to take hold again. So these mass extinctions kind of reset, you know, the order of who's dominant and who's not. So this mass extinction could do that as well. It could provide a reset. So it's, when you hear these phrases like "go green" or these green practices, you know, the Earth is going to be fine. The Earth will survive. The Earth has been warmer. It's experienced mass extinction events before. What you really should say is "go you, go me, go our way of life, go our lifestyle," because that's actually what's at risk. Because all the species that we depend upon, all the animal, plant species, and all a lot of these processes that we depend upon, they will go extinct or be altered, right? And so whenever we can't grow the same amount of food as we used to because our crops are evolved to a certain climate that's no longer present because we have this warmer, drier climate, and there's famine, there's starvation, there's you know, the weather patterns, the climate changes, so there's not as much rain in certain locations, and so there's drought, there's famine and drought, and it causes political and upheaval because you have lack of resources, food and water. You know, civilization breaks down because civilization is predicated on abundant food source. So that's why civilization starts with the founding of agriculture. And so that's really what's at risk. The planet will be fine, as we've seen in previous mass extinctions. It's just us. It's really to protect us. And in order to protect us, we have to protect all the species, plants and animals. Even, you know, people don't think about even insects. We depend on insects for pollination and many other important jobs. It's to protect them because, you know, we have evolved in this world with all these species, and we depend on them. I mean, if they go extinct, you know, our existence is significantly threatened as well. So the Permian Triassic mass extinction should be a lesson for all of us, that we have to change what we're doing, or else, as the old adage goes, history will repeat itself. Thank you very much.